We have two more. We might go a few minutes over, but I hope you'll bear with us. So the next talk is from Chris Mandrell from Southern Illinois University, Carbondale, which, as Eclipse aficionados know, was in the path of both 2017 and 2024. Did you see them both?
I did. I was a member of the team in 2017. And
great. All right. The DEB Initiative.
All right, so this is going to take some audience participation because I redid these slides last night and I forgot to add the NASA partner logo up there. So just visualize NASA partner right there, and that's your part in this in this slide. So, okay. So the Dynamic Eclipse Broadcast Initiative. I'm just going to go through a quick overview of what we did really on the science side of this project. So our purpose and goals. Our main goal here is to collect white light images of the inner corona so we can study the plasma dynamics in this region, where this is where the acceleration of the plasma occurs. And it's a region that we can't normally look at in white light. So the eclipses provide us an excellent opportunity to study this. We're going to attempt to build off the successes of the 2017 Citizen Kate experiment, which you can find results summarized in the paper by Matt Penn, acceleration of coronal mass ejection plasma in the low corona as measured by Citizen Kate experiment. Again, low corona, that inner corona area we can't normally look at. And this is a stacked HDR image from one of the teams that was used for the processing, and we're going to try to recreate this for this eclipse. And we're going to expand on what they did in 2017 with Citizen Kate, because we're going to have a larger volunteer footprint because we've reduced the cost of the equipment so we can get it to more people. It's more portable, and we streamlined the training. So instead of having in-person meetings, we're now doing it all online, and they have to look at my ugly mug doing videos, telling them how to do everything. We're also going to try to incorporate near real-time broadcasts of what's happening across the path, even or out of totality and partiality, so that people who just can't get somewhere to see it or are fully clouded out can see what other people are experiencing. And that was a big part of the development of the project. The data. And you're like, hang on, Chris, we haven't talked about the citizen science at all. And because we don't have very much time, what we've done is Julia Kamenetsky and I have kind of decided to split this load, and she's going to be doing a presentation for session 220, where she's going to have another brief presentation, but she's going to address more the teams, who was there, what they had to go through to get to where they could collect the data. So I highly recommend that you treat that as these are all one part of one presentation. But what did we do? Well, we looked at two types of data or images that we collected. The first was during partiality, we collected 1,000 by 1,000 pixel 15-second SIRS or movies that were on a 1 minute cadence. So we're looking at 15 seconds every minute, and that gives us 45 seconds to process those movies to where we can get high quality images from relatively low quality videos because of the sort of quality of our equipment. And that is useful for the real-time feeds. And you can still see some of the Eclipse images on deborah.physics.siu.edu, even though we are moving to a different phase now, so some of those are going away. But it also serves for scientific purposes because we now have solar photosphere images from all the different teams where we can look at the location of sunspots on their sun, and we can calculate how much we have to rotate them to put them in alignment with the other teams. So it is useful for us from that. And then we have full resolution FITS files in a sequence of 5 exposures that we're going to use to make our HDRs. I'm only showing you 4 here because it turns out that the exposure we selected for the 5th one completely washed out the frame and was not usable, but we're still getting good data from the 4. So now we're going to analyze it, and what we have to do is create an HDR from the set of 4 fits, and you can see here tons of artifact from just an HDR. So what useful is that? Well, we have to clean that up. We're going to have to subtract darks and flats and do some wiggling around, playing with some numbers. But then we get a cleaner image that also allows us to now look for a star in the star field. And then this allows us to do some calculations and say how many of these HDRs can we stack while looking at the movement of this and the limb of the moon and the sun. How many of these things can we stack and still have an acceptable amount of drift in our image over time? And what we've found this day is that we can stack 6 HDRs, which are already a stack of 4 images. We can stack 6 of those to end up with a 0.83 pixel to have an acceptable amount of drift. So now you do that, and there's a whole bunch of nonsense going on. These are actually 2 cleaned up versions of 6 stacked HDRs, and they've been processed a little bit further. They've already had their radial gradient removed, which is just, these are 2 different mathematical processes of cleaning up the way the image looks as you get further from the center. And so there's still, we got to decide, is this one of these the way we're going to go? Is it going to be a combination of these? And then we still have these weird rings in here. Well, those aren't some artifact we can just magically remove. That's due to a nonlinearity of the equipment. So we have to now go back and map out the behavior of our camera, telescope, how it reacts at different exposures, create a nice plot, and then we can delete that out and correct for that different artifact. So what's left for us to do, obviously quantify that nonlinearity I was talking about in the equipment so we can clean up that radial flow there. We've got to calculate and catalog the rotation of all those solar photosphere images from the teams so that we can get everybody lined up angularly correctly. And then all of that done, then we've got to go look and see, was any of this useful? Was there actually an event? Was there a jet, a flare, a CME that we can then apply dynamics to study and get some of our science out of? So that's what I got.
Thank you. We'll take one question if we have one question. All right, well, I'll ask it then. I know you didn't want to go into the data too much, but what was the general setup? Like how big a telescope, small a telescope? Were they using a CCD camera or a DSLR, that kind of thing?
Well, we had and I don't have anything here to show you. It was ASCAR 180 Pro telescope, 40 millimeter refractor with a CCD camera, with a equatorial tracking mount, and then we used SharpCap to collect the data. We used Planetary System Stacker to wavelet correct the data, and I had to do the other. There was a lot of stuff there.
Great, thank you. All right.